Okay, so let's get started. So it's I think this is the third lectures on features, right? So we talk about corners. First we talk about edges, we talk about corners and how to track the corners over time. And today we're going to talk about like feature detection and how to describe the local regions. This is called interest points. And this can be used whenever you put out your form and capture a panorama, it's running algorithm like this. Okay. All right. But before that, I want to, because this is related to your homework 2, which like y'all just described, I want to give you a kind of maybe a review of what we talked about so far, and specifically on how you actually make things work. Right. So overall, you want to detect the key points, right? The corners. And the way you detect a corner is that you want to find the location of pixels where if I move if I have some offsets to along that pixel, it will give me a large arrow. And that is where the concept of that those points are easier to track. Okay. And the way we try, like the derivation we have is that we define an arrow function, basically says that if I have a patch, if I move this patch a little bit, what's the arrow? And we can, if you apply parallel expansion, we will arrive at this equation, right? That arrow function looks like this. And this gives us a very efficient way to compute what the arrow function looks like without actually looking at all the possible shapes. Okay, so which means that we only need to characterize these 2x2 matrix, right? Which means that okay, if I take an image, then I will do is that suggest in the code you will want to compute the x gradient and y gradient, and then you compute the x and y, so that you can see that what we are doing is trying to get the values of that 2x2 matrix. And this 2x2 matrix is for every pixel. For every pixel, you can, once you have this, for every pixel, you have that 2x2 matrix. All right, does it make sense? And then from that 2x2 matrix, you can start to compute something, right? Compute something. In this case, what we did is that you average them, right? You average them, you could, I think the code is, you could do simple thing that's just summing up, or you can do the Gaussian blur, right? Both are the same thing. Okay. So once you have this, you get something, this is the output, right? So, and then ideally what you want is that you want to find the 2x2 matrix, and you want to find the minimal eigenvalues. That is the scale of the change such that if you move along the smallest change, all right? If your direction, so basically the idea is that even the direction that induces the smallest change is still large. And that is the concept of corner, right? So you want to find this lambda mean. And then you have this non-maximal suppression and find the corner. Okay, so that's basically, this is the example of a corner detections. All right, but what you will find is a bit weird is that this is called Shikamashi corner detections, and basically find the minimum eigenvalues. But in the actual implementation, we ask you to do something more efficient. That is the Harris corner detections. Okay, and there it's basically computing the ratio between the determinant and the trace. Okay, and that's also, it's just an approximation of what original corner detection is doing. Okay. And of course, yeah, so we talk about these different invariants. It's fully invariant to rotation, it's fine invariant, partially invariant to intensity changes, and non-invariant to scale. And the last thing it will motivate the introduction of the interest point. Like, how do we get something that's invariant to scale? All right, question about this part? So this part should be relatively easy. This homework 2, like you should be able to implement this without much problem. The second part is where in the past some student will be a little bit struggle. So that's why we have all these helper functions in the homework 2. But basically, kind of, if you understand the basic concept, then it should be fairly straightforward. So the basic idea is that you have 3 assumptions. The first 2 assumptions is that the pixel brightness across frame doesn't change, right? So the same color will be the same color in the next frame. Okay. And with that, we talk about this. You have this from the first brightness constancy, you have an equation, but you can make further assumption if you assume that the motion is small, then you can use tire expansion so that you can get this equation. And now last time we talked about when you have one equation but 2 unknowns, then you couldn't solve it. And therefore, the way to do this is to assume that nearby points move similarly, and that's a spatial coherence. And therefore you can write many equations, right? Many equations. In this case, it's 9 equations because they have 3 by 3 window, 9 equations, and only 2 unknowns. And the way you actually solve for this motion u and v, that's the xy displacement, is to formulate this as a linear system of equation. And then once you have that, you can solve for this with this square, right? You can put this, and you can see this is the things you want to solve. And you can see that this matrix is exactly the same matrix that we see earlier, that 2 by 2 matrix, right? That capture the local gradient statistics, the x gradient square, y gradient square, and the xy multiplication, right? And it's the same matrix because if you look at this A transpose A, this matrix, it will be able to, you can solve this linear system equation. Basically, you can figure out what the motion is if this matrix is invertible, which implies that the minimum eigenvalue is not close to 0, right? If it's close to 0, then it's not invertible, right? So it's everything is, these are all connected. So the way you solve this is that you just inverse, apply this inverse to this guy, and then you're done. Okay. So yeah. Okay, say that again. Unknown is the u and v, right? So in the equations, what we have is that we don't know what the motion is. Yeah, and this equation is coming from the fact that we know that this pixel, the color of this, the intensity of the XY location of the first image is the same intensity. It's the same. Okay, it's probably. It's the same intensity of the pixel at x plus u and located at x plus u and y plus v, right? So shifted u pixel to the right, shifted v pixel to the up or down. Okay. So that is a window that you could decide. That's a hyperparameters, right? So that's a trade-off. If your window is small, then it could be noisy, but you are able to track more fine-grained features. But if your window is large, then it will be more reliable. But if you have some occlusion boundary, then you will have problems. So it's a trade-off. Okay. All right. So the key again here is that you have a u v from the first 2 assumption. You can derive an equation that tells you what a u and v must be. They must lie on a line in the u and v solution space. But because you couldn't pinpoint a point in the u and v, you don't know what the u and v value is. If you know that solution is just on a line, because all the points on the line is also a solution. so there's ambiguity here. So you need to resolve that ambiguity by using this assumption. Okay, make sense? Right? And then from this, you can formulate this as a least square solution, and you can solve it. So you have again, but if you only look at one pixel, based on the assumption, based on the knowledge that this pixel will have the same color for the XY location and the X plus U and XY plus V location in the next frame, and the parallel expansion, you give this equation, right? But now, because you have this trouble of having two unknowns, but only one equation, you couldn't solve it. And therefore, you make another assumption, say that, okay, nearby points move the same, okay? And this will give you more equation, but they share the same U and V. Yeah. And the way and now you have a collection of equation. What you do is to reshuffle this to give you a linear system equation. That's just writing this down more conveniently. And from there, you know there's an unknown, that's a D, that's the motion, U and V. And you have something that's known, that's these guys, X gradient, Y gradient, and this is temporal gradient. Then you can use the tool you have in linear algebra to solve it. Okay? But there's a condition, right? So the condition is in order to solve this, you need to make sure that this A transpose A, this matrix is invertible. Okay? So that's basically the overall concept. Right? Questions so far? All right. So, yeah, so this is the process. You have two frames and you compute the X gradient, Y gradient, and a temporal gradient. So temporal gradient is just take this frame and the next frame and you just minus them, right? Compute the difference. Okay. So once you have this, you similar to the previous stage, you need to prepare the X gradient square, Y gradient square, and XY gradient, and this you also need to compute the IXIT and IYIT. Okay, so you basically prepare all the things you need. In the previous case, you only need for every pixel you only need 3 numbers, but here you have IX square, IY square, IXIY, and IXIT, IYIT. Okay, the purpose of this is to be able to set up this equation. For every point, you have this equation. Okay, that is how you can solve the motion. Right? So if you look at this, every point, every entries in A transpose A, these you can grab numbers here. Okay. So with this, you just that's how you can solve this. Make sense so far? Right? All right. And then we say that because this algorithm only works when your assumption is valid. Your assumption, the biggest assumption here is that U and V are small. But in reality, it may not be small, right? Because if I'm moving very fast, you are not capturing the video with a high-speed camera, right? If it's like a few pixels away, then it's not small motion. So you need to compensate that small motion, right? So you need to basically take a problem that is not a small motion into something that is a small motion so that you can solve it, because your algorithm only works for small motion, right? So that's a key idea. So the idea, two key ideas to solve this. One is the iterative refinement. Basically says that I know that my algorithm here only works for small motion, and because it's not, but the actual displacement is not small, and therefore we just run this multiple times. Okay, iterative refinement. So you start with the initial correspondence as x1 y1 as 0. Then you update this and you compute the temporal gradient, and then you solve for the UV. And once you have a new UV, basically you know that the point, the motion is actually moving to a certain direction. Then you will update this guy, right? Update the IT. You can see that the only thing that depends on the U and V is the IT, right? Is the IT, the temporal gradient. Then you solve for the new V again, right? So you just iteratively solve this. Yes. Yeah, step 2. Right. Step 1 is just initialization, because initially I have no knowledge about what the motion is. So I just assume that it's the move, right? I assume that it's the move that U and V is 0, 0, 0. And then I can kick off the iterative estimation process. Does this make sense? So it's like I know I don't know the motion, how many pixels are there. I don't know the motion, and therefore, but my algorithm only works for small motion. So maybe it would estimate 0.5 pixel. Maybe the motion is actually 5 pixels away, but maybe my first estimation will be just 1.5 pixel. And then, but when I do that, I can re-estimate the IT, and then I can estimate this UV again. Yeah, add it up to the, like, I couldn't do this in one step, and therefore I do this in multiple steps. It's possible, but in general, like, it will converge to the actual motion. You can see that, okay, imagine this, right? This temporal gradient, you can see that the temporal gradient is the corresponding pixel on the next frame, x pawn, y pawn at t minus t plus 1. This is the corresponding point in the next frame minus this point, okay? Imagine that you actually land up at the correct x pawn, y pawn. What is this value? Based on the brightness assumption, brightness constancy, this guy will be the same as this guy, right? It's basically it will be 0. Okay, so if you have the correct motion, then IT will be 0, 0. So if you look at this equation, okay, you are solving U and V with this metric transpose, and if IT is actually 0, 0, then the whole thing will be 0, 0. Okay, then what is the solution to this linear system equation? UV. I have 2 by 2 matrix times UV equal to 0, 0. That 2 by 2 matrix is not 0. Then what could be UVB so that I get 0, 0 as the output? Yes. UV must be 0, 0, right? So this means that if you find the correct motion, then it will converge to 0, right? Then, which means that you won't update anymore, right? Because your U and V is small enough, it is very small, close to 0, and it won't update. So this is the intuition. Yeah, when the IT is not large, then you need to kind of find, basically it tells you like how do you find the motion so that it can compensate that error. Yep. Yes, yes. I1 is from the first frame. That is from the gradient of the first frame. Not different. Not the next frame. So which means that this can be very fast, right? The 2 by 2 matrix, and you compute the inverse of that 2 by 2 matrix. But that is from the first frame. So once you compute this 2 by 2 matrix inverse, you just cache it, right? You just save it in the memory, and this iteration solving the least square solution to get U and V is just a matrix vector multiplication. It's very cheap. Okay, so even though it's iteratively solving this linear system equation, but because this guy does not depend on this 2 by 2 matrix does not depend on the U and V. Okay, but IT does. All right. Okay, so that's the first idea. you cannot get it because your algorithm only works for small motion. You cannot get it in one trial, and therefore you have to do this multiple trial. Yes. Yeah, so you started with U and V. You start with U and V. Your initial guess U and V is 0, right? Because you don't know what the motion is, and once you estimate it, you get a new U and V. Then you can update your positions of x prime, y prime, right? Maybe this is the 1 pixel to the right and 0.5 pixel to the top, to the up, right? And once you have this new things, x prime, y prime, then you can re-estimate what a temporal difference is, okay? And then you estimate this, use this equation, okay? And you can see that it will converge because if this IT, this x prime, y prime is, if this guy is very close to IT, this guy, it means that your temporal, your brightness constancy is minimized. And you can see from the, like intuitively, you can see that this guy is 0 everywhere. Then the whole thing, this U and V will just be smaller and smaller. So you can kind of, you get to the, when you iteratively estimate these things, you will get converged to 0. Okay. And actually, this is how you can implement a terminated condition, right? When your update U and V is sufficiently small, then you break out the loop. You don't need to estimate it anymore. Okay. All right. So this is the first trick that you use the iterative refinement. Again, it's because that you know the assumption when this algorithm will work. The algorithm will work only when you have small motion. Okay. So the second assumption, the second thing is that because when you deal with this motion is very large in the original image space, right? If your image is actually high resolution, it's very large motion. So the second idea is that you create this force define, okay? Any large motion in a high resolution images become very small motion in a low resolution image, right? Because it's just not many pixels. Okay, and that's a very, very simple idea, right? And the idea here is that instead of trying to estimate the motion directly in a high resolution image, because you need to estimate like a 30 pixel wide, but if you work your way down from the small resolution, this is actually a very small resolution. The motion here in the lowest level is actually small. Okay. And what you do is that you start with here, and then you try to estimate your Lucas kinetic algorithm. You get an estimation of U and V in total aggregated motion. Okay. Then you update this guy, and then you can upsample your solution. You make a in this low resolution images, the algorithm will work. Okay. Algorithm will work because now your motion is small. Okay. And once the algorithm works, then you have a better guess for the next level. The way you do this is that you just upsample your solution here, and then you get you can take a new setup. You move up to the one level, and then once you estimate solutions, and then you can move up to another level, and then so on. Okay. And the reason why you move out another level, it will still work because you have a pretty good estimation from the previous solution. Okay, so you kind of like initially, I don't know what the actual large motion is, but I gradually refine my solution. Okay. Yeah. Yes. Yes, you will need to do that. Yeah. Okay. So it's a very simple idea. You can see, but it actually have a very large impact to the computer vision community. So I want to share the person who and his students who invent this algorithm. That let's see the story. Basically the idea is that it's very, very simple, and then what they found is that they thought this is nothing, this is really trivial, and they even don't want to publish this paper. Okay, let me see if I can play this.
Small displacement u. And now you see u, which is unknown, comes out of that function f. And if you put that fx plus u substitute in the original one, then eu now becomes a quadratic function of u. Now we know minimum or quadratic function is here, which is computable. Even high school student can do. Now, of course, we're talking 2 dimension, so it's a little more complicated, but you can get explicit. This should work, Bruce said. We should write a paper, he said. I said, no, I don't want that. And Bruce asked, why? I said, Bruce, this is not new. You see, newness. I was thinking new is important. This is not new. You know, Taylor expansion has been known 300 years. This is not new. And what you did is the derivation, that's high school student can do. And I don't want to write a paper on a Taylor expansion and derivation, which high school students can do, and then my reputation will go down. You should not write a paper. And Bruce was very persistent. We should write a paper. So I told him, okay, you can write a paper, but make sure you write a paper in a very obscure place so that nobody would read it. And indeed, we wrote a paper and we never published any journal paper, never. Guess what? That paper turns out to be the most cited paper of my whole life. Indeed, more than 10,000, probably more, sightings. The biggest cited paper. And if Bruce listened to me, I think Takeo Kanade today did not exist, I think. So since then, I always tell students, what your professor says is probably wrong. So don't listen.
Right. Yeah. So this is I think it's a pretty interesting story that shows that sometimes it's very simple things actually, and it works. It doesn't really matter how trivial that looks like. Okay. All right. So any question about basically homework 2, these two problems? Yeah, homework 2, basically you implement this feature extraction, like one feature extraction is a corner, and then you will talk about then you will look at the how you track over time. Okay, so it's actually everything is connected. So look at the house example. You will detect the corners and you will track them over time. That is, you have a camera that move around the house, and you'll be able to track them over time. And later on in homework 3, you will actually take the trajectory from the trajectory of the tracking. You will be able to reconstruct a 3-dimensional model from the trajectory. Okay, so that's the everything is connected. Okay. All right. Questions so far? Okay, so let's recap what we have talked about so far in the module 2, right? So from a single image, that based on the tools we have in image filter from the module 1, what we could do is now we take this image, we could potentially extract features, right? Like lines, this edges detections. And then we also can detect key points so that we can track them over time, right? So what the main limitation of these corners is that they are not scale invariant, which means that if I take this, like this is the photo of certain resolution, right? If I go out and take another photo of the same building, I wasn't able to repeatedly detect the same feature points, okay? It's because that the corners, sometimes in this scale, the corners are there, but maybe in a closer scale, the corner disappear, right? Or it doesn't, my corner detection algorithm is not able to repeatedly detect the same point, which means that I couldn't really match them if I have images that are of different scale. Okay, and therefore we need to fix this, right? Because a lot of time you want to be able to match or build up correspondence between images that are taken from different scale. Okay, so this is where we need to talk about the feature detections, right? So this is the interest point that people call it interest point. Basically, you want to find location that are interesting, that has something going on in a particular scale, right? So what you see here is a bunch of circles that have different sizes, and that sizes correspond to the local scale, right? We'll talk about that, what the local scale looks like, and the local scale, and you can see that they have these bar that tells you what the dominant orientation of the local regions, which means that if imagine this image, and if I take the image in a slightly oriented way, the detection algorithm will be able to detect the same region and detect the same, it will compensate that orientation. If I can do that, then I will be able to match the key point extract from image 1, key point from image 2. I will be able to find a matching between them. Okay, and this is important because from the matrix you will be able to do instant recognition, right? Every time you pull out a form and then capture a photo, and then you feed into Google image and say find similar image, and that is running similar things here. They are trying to find interest points so that's similar to the database, right? You can do the search from multiple photos and you can do triangulation, then that's give you 3D reconstruction, right? So that's why we want to talk about interest point. Okay, any questions so far? Okay, so the goal is to really find points that are scale, like the goal is to make sure that our detection is scale invariant. Okay, so look at this. Imagine we want to find a corners. Okay, so to find a corner, we don't know what is the actual scale, right? This could be this is an edge, and this could be a corner, and now this becomes an edge again. Okay, so we need to have the idea here is that I need to have some measurements that will capture that if I test on multiple different scale, and which of the scale will give me the maximum response. Like there was I want to find something that's sensitive to this response. Okay, so that I can maybe say, oh, this is the corner. This is the interesting part of under this scale. This region is interesting. Okay, so yeah, so basically you need to be able to find the location and the scale. All right. So once we have this, then we are able to be able to match images from capture at different scale. All right. So in this case, basically what we want is that okay, from image on the left and image on the right, they correspond to different location, right? But then you can see that they are capturing on different distance from I think this is wall, and we need to define. Basically, we need to have a way to characterize what is the bounding box on the left and the same bounding box on the right, so that they match up together, right? Because if I draw a different size of bounding box, they don't really match up, right? Because the different scale. So what we will do is that we need to have a kind of computation that tell me what is the score of that the scale, right? So for example, what you do is that if you have some scale, you try out multiple scale, right? You try out, you can see that I'm trying out multiple scale, and then you will find that that score, right? That score is very product multiple scales. You can see that these guys peak at this location, at this point scale, x-axis is a different scale you test it. And this guy match this one, and this guy, they rise up, and then the peak is at the letter scale. Okay. And from there, you see that the peak is corresponding with each other. All right. So by doing this, you are able to not just determine where it's basically XY location of the key points, but also what is the size of that key points. Okay. Yes. Yeah, we will talk about that later. Yeah. So just the key idea is that we need to have a function that tell me that if I have tried on different scale, and that function will have different maximum at different location, at different scale. Right? I want to have that function that is sensitive to the scale. And the goal is to make sure that when I detect a feature point, I'm not only detecting X and Y location, I only talk about the scale. I only figured out what the scale of those things. Okay. All right. So this is the actual functions we do. Basically, it's like it's called difference of Gaussian. Basically, they have you compute a Gaussian filter, and you with certain size, and you also compute another Gaussian filter of the other size. So what this looks like is the following. Okay. What this looks like is that essentially is trying to do is that trying to average something in the middle, and minus the average of something the surrounding. Okay, essentially it's trying to say is this regions has a sufficient contrast between these circle and the surrounding. Right, that's the filter we are using. Right, so you can see if I apply these filters on the different blobs, right, different regions, you'll find that if I have a small blob, then these filters, only this guy will have high response. Okay, if I have this blob, only this guy will high response, and if I have this blob, only the large filter will have high response. Right, so I can determine if even though you have images of the same thing, that's a blob, that's a circle, but the different scale, I can use that filter to pick out the right scale. Does it make sense? Let's see. Okay, so I use this. Let me see if I can say something. Okay, so basically the idea is so far the idea that we can use a filter to detect a scale. Basically, that's the main idea behind this. And that filter we use is called difference of Gaussian. Right? It looks like this. You can see that what they're trying to do is that to average certain regions and minus other regions, surrounding regions. So if I am the filter, the size of the filter match the blob you have, then you have a large response. Okay, basically, if I have a contrast, right? Imagine that if I use a large filter here, apply to this guy, it doesn't have any response, right? Because this large filter is averaging over larger area. The average center of the center regions and minus the surrounding regions. So it's trying to capture the contrast between the center and surrounding. Okay, and if you apply this guy into this guy onto these small features, it doesn't have a response because you just average too much stuff. Only when you have this small filter on top of this, only when your filter has this correct scale, it will light up that, oh, this is actually, if I average the center of these regions minus the surrounding, then you will have a high response. Okay, you have something like this, right? So it's you can think about this as a way to select the right scale. Okay, so what you do now is just try to find implementation that we can do this efficiently. How can I construct this difference of Gaussian blob detector? Okay, the way you do this is you have essentially an image that's slightly blurred minus that's more blurred, the image that's more blurred, right? So basically, Gaussian filter image with some sigma, and this is the sigma is higher, larger. Okay, and that will give you something like this, right? It will give you something, this is high response and low response. All right, and this is where the Gaussian filter could be very useful, because if you want to construct a Gaussian filter image with a larger filter, what you do is to just repeatedly apply that Gaussian filter, right? So this is the process. You basically start from the original image, and you apply a Gaussian filter repeatedly, and then you compute a difference, right? And so you can easily, this is an efficient implementation of that block detectors over multiple scales. Does it make sense? Originally, if I want to detect multiple scales, like say 10 scales, then I will need to apply the same filter, like different size of that filter multiple times. But that's costly. So what I do is that I just repeatedly apply Gaussian filter. That's very cheap. That's separable, so you can apply this very efficiently. And I just need to minus compute difference between the successive layers. Make sense? Yeah, it's also a Gaussian, because if I blur this enough, then I can just downsample it and then the next level. And I can, it could be very efficient. So it's just an efficient implementation of that block detections. So this will tell me whether if this response is high, they will tell me that there's something interesting at that scale. I want to find not just the XY location, but also the scale. Because we're trying to find the corresponding, like, how do I determine what scale is this, right? The way we tell, this is the right scale to describe these regions is that imagine that you sum up the regions within this bar and minus the region outside this bar. It will be the maximum, right? Because it's dark inside and bright outside. Okay. So it has the most contrast. Okay, and so what I'm trying to say is that filter captures the most contrast of these regions. Okay, if you can find that, and this is very selective, right? Imagine you can see that it only works when you pick the right filter size on top of that, and that will give you the maximum contrast. If I use a smaller filter on this, it will still be black, right? Still no response. Only when you have the average within these regions and minus the region outside, that will give you the maximum response because that's the largest contrast. Yeah, yes, exactly. So basically, what I'm trying to say in the next slide is that if I want to implement all this, it's costly. And I can implement this by just saying that I just repeatedly blur and minus compute this. It's just efficient implementation of what I just said. Yeah, it's a different size. Yeah, so you can see that this basically, what I need to do is I just take the input image, blur it iteratively, okay? Iteratively, when you iteratively blur, this corresponds to applying a larger Gaussian filter, right? And then you compute the difference. That essentially is the computer difference that it corresponds to different filter size. Okay, right? So, and with that, it will give you this gives us the signature of a local region and not only the position and the scale, whether that's an interesting region or not. Okay, so what we do is the following. If I have this thing, okay, again, this is a image, and you have this type of filters, and they apply the filter across multiple scales, and you get something like this, all right? So what it does is then you basically take this value and threshold it. If this is if it's a large response or low response, okay, and that tells you where it's an interesting position and the scale. So what you do is that for every, so you have now you not only have an XY location. Remember that in the corner detection for XY location, you do a non-maxima suppression. Basically, look at every pixel and see if the surrounding window is whether it's my response is the highest within the surrounding window. If yes, then keep it. If no, suppress it. Now the non-maximum suppression is 3D. Not only X, Y location, but also along the scale. So with this, you will be able to pick up the location and the scale where that response is the highest. So that's how you get something like this, right? You can describe all these regions are some regions where it has a high response. And that response is not just the XY location, but also the scale. If you have a slightly larger scale or smaller scale, that has a lower response than this particular scale. Okay, so what I'm trying to say is that you will do non-maximal suppressions, not just along the X, Y location, but also the neighboring scales. Right, so you can see that if I imagine I have a 3x3 window, and the and also check 3 scales. What I do is that you take these values, and you only keep that response only if it's this pixel has value that's the highest, that's the maximum response over 27 numbers. Okay, so you do non-maximal suppressions across space and scale, which means that whenever you detect these things, it means that these are unique positions, not only unique in terms of XY location, but also unique across scales. Does it make sense? Yeah, similar to finding a corner, but it's just an extension of a corner detections. I'm not just interested in finding the corner, but I'm trying to find location where you have that has a unique scale. Okay, and you can use this to many other things. Okay, the idea is that imagine that your database, you want to search an album or book, right? Your database has a one scale, right? You cannot save multiple scale. You have some feature description about a particular thing, and those has a specific scale. And you cannot control how you capture your query image, right? Your query image has a different scale. And therefore, you need to make sure that you can repeatedly detect that features at the correct scale. Okay? Yeah, that's why we need to use this. Okay? Okay, so this is called a feature detection, right? I want to give an image, I detect where the location is and what the scale of that. And then when we try to match one image to another image, I need to describe that image, local image, okay? The simplest description of that local image is to say, okay, I want to describe a particular circle, maybe this circle. But the simplest way is to draw a box and then grab that patch, right? That is my simplest feature description, right? In this patch, maybe it's a 16 by 16 patch. If it's 16 by 16 patch, then in total, you can vectorize it. So in total, you have 256 numbers. And you can use that 216 numbers to describe, you can think about this as the signature of these local regions. Okay? But that itself is not reliable. And therefore, we need to design a way that we can reliably detect the reliably match across different regions. Okay, so and this brings us to the, so basically this is the criterion that we need to be robust, we need to be descriptive, and so on. But the reason why we cannot just take the grayscale patches, because they're very sensitive to lighting changes, right? I take a picture, if I change the light, if I change the lighting in this room, your image will become completely different. So you cannot really take the grayscale patches. So what's more robust is the gradient information, okay? Specifically, the orientation of the gradient, okay? So what you do is that you have this local regions, like this is the scale of something you detected, and what you do is the following. You compute the gradient. The gradient is x gradient and y gradient, and that x gradient and y gradient give you the orientation and the scale, right? How large is the gradient along the x direction? How large is the y gradient along the y directions? So you have a local region that has a distribution of the gradients. So what you do here is that you first, with this information, the first thing is that you can compute a histogram to see which of the gradient, like basically what is the histogram doing is the following. For each gradient vector, you have the orientation, right? Then your orientation is ranging from 0 to 2 pi, okay? Then you vote in that if there's a gradient along this direction. Let's say this is a 45 degree, and you go to the beam of 45 degree and cast a vote, right? And you do this for all the pixels within the local regions. You get a gradient histogram, and the dominant direction is your feature directions, okay? Which means that because this direction does not change if I take a picture, no matter how my orientation is, okay? Then I can make sure that no matter what the orientation of the picture, I will still be able to tell what's the scale, position, and orientation. Okay? All right, once you have that, you can find the description. And the way they describe this is that in the local region, they break it up into 4x4 chunk. In this case, I show only 2x2. And then 2x2 for each grid, you capture the histogram of oriented gradients. And there are some benefits of this. The first thing is that because you are using a gradient information, remember that we talked about earlier, the lighting changes are very sensitive, right? The intensity of the image is very sensitive to lighting changes. But the gradient, the difference between pixels is not. It's not that sensitive. Right? Eventually, if I have an image, I just add 50 intensity to that image. The gradient is the same because they are trying to compute the difference. The gradient information is more robust to these lighting variations. And furthermore, if I compute a local regions, I aggregate the information across local regions, then it will be robust to spatial shift. Right? Imagine I compute a histogram over these regions to get this histogram. If I shift one pixel to the right, it will probably be similar, which means that if your feature detection is not that accurate, it will still be fine. You can still extract similar features, feature description that allows you to do the matches. Okay, does it make sense? All right, so I know this is a little bit complex, but once you have this, you are able to do feature matching. Okay, so let me try to see if I can. Okay, so basically you have something like this, right? So basically based on one image, you will be able to detect the feature points. So look at this, like every feature point, you have a corresponding scale and orientation. And within each scale orientation, you have a description. So you basically have two things. One is that you have the features, something described where the feature is, the XY location, the scale, and the orientation. And based on that, for each feature, you also have a description about that feature. And that description is using a histogram of oriented gradients. Okay, and that is capture the rough appearance information. Okay. All right, so you can go over the implementation details, and it's very highly useful. People have been using that a lot. All right, so let me try to give you some intuition of what this could be useful. Okay, so given this information, given this image, you will be able to detect all the features, right? So you have a very dense features, and the reason why this is useful is that these local features, first of all, is that because it's local, which means that imagine I want to find I don't know an object in this image. And I have something in mind, like this cover. And I could be the image I am querying maybe occluded, like some part of them will be occluded. But that's okay because my features is local. Okay, so I can still find the matches within the available features I can detect. Now the question is, how do if I have an image in one hand and another image capture another image of the same scene. How do I match them? Okay, so the idea is that if I have an image in image one, if I have a feature in image one, how do I find the matches in image two? Okay, for that you need to find a distance measure of the feature descriptor. Okay, so and then okay, so let me see. Okay, so basically the idea is the following. You have two images, right? Or two images of the same thing. Okay. The simplest idea is the following. The simplest idea is that let's try take image at feature one, that's this patch, and I want to go through all the possible patches, all the possible feature points in image two, and find the closest one. Okay, that's one idea to find the correspondence. Right? The problem is that it's not reliable because here you can see that they have the image has repetitive structures, right? So which means that this, even though this looks very similar locally, looks very similar, but they do not actually, it's not actually a correspondence. Okay, so there's an important trick in the original paper. What they said is the following. Like you cannot just take the the feature from image one and find the closest match from image two and declare if they are small enough, the distance are small enough, then declare that they are matched. What you need to do is to find the following, is to find the two nearest neighbor. Okay, so what it does is that you take feature in the image one and find the two closest neighbor in the image two. Okay, so what you do is that you compute the ratio between the distance to the closest neighbor and the distance to the second closest neighbor. All right, so why do you want to do that? It's because if your two nearest neighbor, if this ratio is close to 1, it must be less than 1 because this is the first neighbor and this is the second neighbor. If the ratio is high, what does that mean? It means that the second closest neighbor is also very close compared to the closest one, all right? Which means that it's an ambiguous match, right? If the ratio is small, what does that mean? It means that it's very reliable because I did the closest one, and even the second closest one, I find the closest match and have a certain distance. And even the second closest one is very large compared to the distance, which means that it's a reliable match. So you can use this criterion to not only find matches, but also more reliable matches. Okay, that's called two nearest neighbor heuristic. It's a heuristic, but still used today. Yes. What ambiguous matrix means I can use that ratio to tell me whether the matches are ambiguous or not. The ratio is, if the ratio is large, close to 1, then it's an ambiguous match because the second closest and the first closest are similar. We don't want ambiguous match. Yeah. So here's the kind of the matrix looks like. If this is the model, like for example, I want to find a particular things, and you can show that these are the good matches. It's still, even with that, you still have some wrong matches, right? You can still find, okay, see that this is wrong matches. But with the two nearest neighbor rule, you actually can rule out a lot of bad matches. Okay? Yes. You couldn't really find it. Like that is not a good matches. But if you only look at the closest one, nearest neighbor, it will give you a lot of false positive. Right? It will give you a lot of matches, but that's actually not true. Like, just if you want to find one specific yeah, so you'll need to do like, which means that if you this repeated structure, you couldn't really find a good matches. You will have to rely on something more distinct that can help you to figure out the right matches. Okay. Right, and you can see that in another picture, even though they are different orientation, you can see that in this case it's very reliable, right? All the matches are probably correct matches. And with this, you actually can be very, very useful to figure out kind of alignment. You can do retrieval and all these other applications. Yes. Does this work at like Scratch? Yeah, it will work to some extent, but it's not perfect. Okay, so auto plan orientation or rotation is the hardest part, right? But in-plane rotation, scale changes, they are pretty robust. Okay. All right. So the problem here is that there's still wrong matches, right? There's still outliers. Okay. So in the next lecture, we will talk about how do we deal with these outliers? How do we make things robust? Okay. Thanks.